Hello and welcome to Happy Maths Hour. I've just finished Mindset Monday and I can't find Toni. I don't know where Toni is. We've lost Toni. I'm hoping I've sent her the correct link. Maybe I must just go and send her the correct link, and then I'll introduce myself again properly because Toni's not here. Let's see, invite. See, it gives you a little bit of insight to the back thing. Now it's welcome to Happy Maths Hour. Today's all about spirals and helixes, or helices, helixes, plural helixes. And copy to clipboard, make sure I've sent her the correct link because that's not working. It is 5 o'clock, isn't it? 5 o'clock, might have to call her. Or had she called me and I hadn't maybe noticed? That goes there, that doesn't help me. There's my phone. Has she called me? And no evidence of, is there evidence that no, she hasn't called me, so maybe I'll call her. Let's see what happens if I call Toni. So what we're going to do, we're doing helixes today. I'll do the jingle and whatnot while I call Toni. And if I can find it. Here we go. And here we go here. Right. I'm going to do the jingle and see you after the break with Happy Maths Hour, and it's all about spirals and helixes. We're going to go round and round in curves and have lots of fun doing it, hopefully. Here we go. And, oh, I can't hear because I've got it on mute.
I'm backstage waiting.
Oh, you are backstage. Okay, I see you now. I see you.
Been here a while. Well, at least half a minute.
Have you? Oh, okay. Hello. Everyone can hear you, Toni. So we're going to go to the break and then we'll be... Hello and welcome to Happy Maths Hour. Ooh. With Toni and Caroline. And Toni's got another amazing presentation ready for us on all about spirals. So am I starting with the spiral then, Toni? Is that what we're going to do?
I think we should start with your bubbles, Caroline. How about that?
Okay, now what I discovered earlier, because I did test them earlier. So what I'm going to do is I'm going to put my visualizer on because let me just do it because I've taken, if you notice, I don't have my screen on at the back in the background. So let's see if we can do it. Oh, that's not bad. That actually works. If I get myself out of the way, can you see all those curved surfaces? Oops.
Oh, I can see a bubble in there. There's a bubble in there. That's great.
There is a bubble, but you can really see now this is not a spiral. It might look like a spiral staircase. You can imagine that as a spiral staircase going up, and there is actually a bubble going all the way from the bottom there all the way to the very top, but it's not a spiral. We're going to find out what it actually is. This is a spiral. It's a kind of a wonky spiral. It's definitely not proper round, but it is a spiral. It's notice it's two-dimensional. If you look from the edge on, it's more or less flat. I am not I'm not the expert at these things. And can you see the soap film? Isn't that beautiful? And then so you've got both this metal spiral there and you have a soap film spiral. That soap film is very tenuous. But look at that. Look at those beautiful colors. Oh, I do love bubbles. So that
I like it.
Is a spiral. It's 2D, it's flat. And this is a helix. Oh, look, you can really see it there. That's a good one. That's a good angle.
That's beautiful.
That is a helix. And again, both the metal frame and the bubble are both forming a helix of different types. So that's three-dimensional. So there you go. That's the bubble.
Fantastic. Right, so I'm going to share my screen, and hopefully you will see this one, and I hope you can see the slide. Can you, Caroline? Can you see it?
I can see the slide. I'm about to activate it. Adding to stream, and there it is, and sort of. Oh, there it is. Good. I'm going to change the background there.
Excellent. Excellent. Right. Well, we're going to talk about spirals and helices today. And here they are. Here's a picture of a spiral, as Caroline was showing you. It's a flat and two-dimensional. So that's actually a picture of rope coiled on a deck. But you can see the spiral. Look at the knot in the middle, and it goes round and round and round and round. Okay.
And that's flat. You can imagine that is actually it's sitting on. Okay. So it's 3D rope, but it's flat. If you looked at it from the edge, it's flat at the top.
If you took a horizontal slice of that, you'd have a single pane.
A cross section of it, right? Yeah. Mm-hmm.
Now on the right, what you have are 5 different helices. Well, they look pretty similar except for the colour. But as you see,
what the plural is, it's a helices. One helix, many helices. Right, thank you.
Yes, but in everyday language, we call things which are actually helices, we call them spirals. But in mathematics, the spiral is 2-dimensional and the helix is 3-dimensional. And the helix is always a curve on a cylinder. You can see that from the picture there. As it were, around what imagine a cylinder in the middle as the core around which the curve is winding. Okay. And so these are actually, in mathematical terms, not spiral staircases. Rather, they are helices. And they're brilliant because, imagine getting up to the top of a tall church tower or some tower. They take quite a small space, but you don't have to climb steeply. If it was a straight staircase, it would be like a ladder going up the tower. But because it goes round and round and round, you have lots of steps, and each one is just a small step as you go up. So you have one.
The stairwell on the right, the helix staircase on the right, does that inverting thing. It's hard to tell which way round, whether the stairs start facing away from you or facing which way you get on them and which way you get off them.
The bottom lot is behind the rail and the top lot is, well, wait a minute.
No, that's the thing. I don't think they are. I think that's what I mean. I think the bottom lot is actually in front of the rail because otherwise you're getting on them from the corner of the room, which you can't get to. But it does look as though they're behind, doesn't it? It looks as though
well. I mean, it's optical illusions, isn't it? And actually, I think the truth of the matter is, Caroline, what's there is not actually what you see. It's what your brain makes of what you see.
Yes, indeed. Definitely.
So now this is a nice experiment or little activity that you can do, children can do. And there you see a toilet roll sitting on top of my computer. When I took
I've got one that I made quite quickly earlier today as well. You see how that's the size of it. Go on.
So what I did here was to go down the glue line, the crease, with a pink colouring pen and mark that. And I also marked circles in blue around the cylinder. And I marked straight lines from top to bottom parallel to the spine, or the axis of the cylinder. Okay, so let's imagine now, this is an exercise in visualization. What sort of shape will we get when we undo that that toilet roll and flatten it
along
out.
the spiral, along that pink spiral.
Well,
Helix,
along the glue line. Yes, it's
along the
glued
blue
along there.
line,
Yes.
along the pink line.
When it was made from, well, what sort of shape of
Yeah,
piece
no,
of cardboard
I'm
was it
saying
made?
along the pink line. I'm saying along the pink line.
Oh, sorry, Caroline. Glue line, not
Yeah.
blue line.
Yeah. Yes, sorry.
Okay, that's what it looked like. It was originally a parallelogram, not like the label off a can of beans. This time it was a parallelogram.
So this is what would have looked like had it been like if you cut it straight up like the label of a can of beans. And yeah, and Toni's one is far more interesting.
So here what you've got is a toilet roll core flattened out, and the pink lines were the lines along which it was originally glued when it served its original purpose.
And the other lines, instead of being vertical and horizontal, they're now diagonal.
Well, what's interesting is that the vertical lines are still parallel. I didn't space them evenly or anything. I just wanted to show that straight lines are preserved. These are the straight lines are parallel to the axis of the cylinder. So that circles become straight lines.
So the circles are the blue ones. Oh, that one doesn't have a blue one, so that doesn't help. But so the circles are the blue ones, yeah, and they become. I didn't put the bows on there. That wasn't a very good example. Yeah, so they do. They really. Everything's straight. It's no longer a circle. It's all straight. So, and that's got a lot to do with the 3D geometry, doesn't it? It's the cylindrical geometry.
Yes, and the thing about this is that when we think about curvature, we don't teach about curvature in school, but we know a bit about curvature and how it can be constant as on a sphere, and it can change as it does, say, on a rugby ball. Now, a cylinder has zero curvature. A cylinder is, to all intents and purposes, flat.
So geometrically, the surface of a cylinder can be considered to be flat. You can work on it as though you can calculate things as though it were flat.
Yes, it doesn't have any curvature. Although
that doesn't make any sense to me because it's clearly curved. I mean, look, it's curved. What does that mean?
Well, I flattened it out, Caroline, just to show you.
But the point is you can. The point is that even though it's curved, as long as it's a cylinder, you can work out the geometry as though
if it were flat.
Yes. Okay.
And when we flattened it out, the angles were preserved. Notice the right angles between the blue and the green lines.
They're still right angles. Yeah, they're identical. Yeah.
So there's a lot of maths in there. We haven't got much maths in the rest of the talk because there's so many nice pictures. Now remember what the helix is. It is like this screw thread, and those drill bits that you see there are all designed so that they carve into the wood and make a track in the wood, a screw line in the wood. And of course, I was going to introduce a picture on the Archimedean screw. Now, the Archimedean screw is something, as the name suggests, invented by Archimedes, where mechanically you could lift things with a screw, okay? And you see it in a man who's opening a bottle there. You see the cork is being lifted out because the device there screws the corkscrew into the cork and then lifts it out. So that's that is like an Archimedean screw.
Yeah, it's slightly different because the Archimedean screw actually turns around, and what it does is by turning, it was used originally as a solution to irrigation, to lifting water up, to solve a very real irrigation problem, which Archimedes solved a lot of problems in his day. He created a lot of inventions. He's an extraordinary man. And the Archimedes screw, by turning the screw the correct way around, the water would literally rise up the screw, using physics, and then plop, come off the top, and lo and behold, they had running water.
Brilliant, brilliant, yes. So now here's another couple of pictures of helices, the pasta on the left, right?
Yeah, never again. That's helix pasta, ladies and gentlemen, boys and girls. That is for now and forevermore, helix pasta.
And of course, the DNA was discovered by scientists. So they didn't call it a DNA spiral. They gave it its proper name, a double helix.
And you notice that, yeah, go on.
You can see in that blue picture that there are actually two helices there, and they're joined by these bars, and that's a diagram of a little piece of the DNA double helix.
And it is interesting because we did this the first time we did the global mass lesson, didn't we, Toni? And if we create a model of the double helix, it doesn't automatically coil around itself. We had to actually force it. We made it with balloons the first time around, but you have to actually force that shape to stay in shape. So the DNA has forces that hold it in that shape, whereas it all coils. It all coils, very, very. It's like the lungs and the intestines. It's all coiled together, but it's that the fact that it's coiled is if you have a go at creating a double helix, you see how well you can make it stay in that shape.
Well, in case you're feeling hungry, or to make you feel hungry rather, here are some cinnamon buns. Don't they look delicious?
Now, is that a spiral or a helix?
Well, I think you could imagine them flat like the rope, couldn't you? Really, I don't know.
You could I don't think a cross section of it and have
I don't think we need to be too technical here, but anyway, there's another example for you. And the yo-yo, nice orange one for you. You like orange, don't you?
Much appreciated.
And the yo-yo goes up and down. It's a lovely toy, and I think the principle is one of a helix, so I'm not 100% sure about that. Shall we have a jingle before we continue?
Yes, absolutely. I had it all prepped to go, and then I got distracted. Okay,
Let's
we are
continue.
back with happy. Let's tell everybody in case they've been gone. Happy Maths Hour with Toni and Caroline, and what we're doing is it's all about spirals and helices, and we've covered the difference between a spiral and a helix, and now we're finding out more with Happy Maths Hour. Go ahead, Toni.
Aren't these delightful pictures? There's an antelope there with the most impressive and his horns. What do they call them? Antlers.
Antlers. Thank you. Yeah, that's not going to help at all there.
Yes, so, I mean
they occur in nature.
Isn't that brilliant? I mean, they seem to have. I particularly like this picture because his antlers seem to have a helix grooves or markings around them, don't they? The lines going round and round and round them, and themselves, those are the brown marks on the antlers, and the antlers themselves are twisted.
yeah, it's very intriguing.
And he's looking at us as if he wonders what he's looking at. He's quite surprised by whatever he's seeing, I think.
Are you looking at my horns?
I love the markings in the ears of these antelopes. Have you ever noticed? They've got the most delightful markings inside their ears.
I can't say I have. Now I'll have to have a look then.
Now,
so where are those antelopes? Where do you encounter them? Is that in Africa?
Yes, yes. I'm not quite sure of what his name is. I'll have to look him up. I mean, we do know the names of a lot of antelopes, but Alan and I didn't immediately recognize that one. So it's certainly not from the southern part of Africa. So I'll have to find out just exactly what sort he is. Now, in the middle at the top with the red background, you've got the nautilus shell, which has been carefully cut in half, and you can see the chambers of the shell. And as the little creature grows, so he builds extra chambers. And there's something about the way in which he swims, which uses these chambers. So that is a nautilus shell. Got some other seashells below. Some of those are also got this sort of helix or spiral form. And then you've got on the right, you've got two terrestrial creatures. Don't you like the jolly little snail up at the top right, Caroline?
It's really beautiful. It's fully extended, all its antennae and its full body extension there.
But it's got such pretty markings on its shell.
It really does.
So like the antelope, not only is the shell itself a spiral, or yes, a spiral if you flattened it, but also it's got the markings on it as well, which go round and round. Yes, like the antelope's antlers, yes. So there you have some examples from nature. Now we'll have some more examples from nature. Isn't that lovely? Now you can see, look at the big one, the other ones are a little out of focus. You can see spirals there of the stamens in the middle of the sunflower. And careful counting, I'm told, I've never actually done it myself, I have to confess.
I have done it, but it is really difficult, and I have to say I don't remember. But it is. You go cross-eyed doing it.
You do. Well, you can
really
see the spirals, but if you count carefully, there's a Fibonacci sequence buried somewhere in there, and the Fibonacci sequence is like this. The first two terms are 1, and then 1, and then you add those two terms, and then to get the next term, which is 2, and then you add the 1 and the 2 to get 3, and then you add the 2 and the 3 to get the next term, which is 5, and you add the 3 and the 5 to get the next term, which is 8, and the next term is 13, and the next term is 21, and then 34, and so on. So that's a Fibonacci sequence, and we're going to come back to Fibonacci sequence a bit later.
There's lots of flowers that have the same pattern.
Yes.
The sunflower's the most, possibly the most dramatic one, but there's lots of flowers that have petals in that pattern and all kinds of things. It's extraordinary.
Stamens sometimes and the petals sometimes. What about these now?
Oh, well, there you go.
I mean, isn't that rose exquisite?
Yeah.
And you can see it unwrapping or wrapping down to the middle, as it were. As the petals are arranged, they're arranged in a spiral rather beautifully. And the one on the extreme right is a succulent or cactus-like thing, but you can see that again as a spiral.
Yeah.
And that's a vegetable just beside the rose. Not quite sure. What is the name of that?
It's a type of broccoli. I don't remember the specific name of it, but it's a type of broccoli. It's got its own
special name, I know.
Yes, it does. Yeah.
You can see you can again see the spirals there, and on the left again. So there's, if you look, there's many flowers, and succulents and cacti, and sometimes it's the stamens, as with the sunflower, and also the petals. Sometimes petals and stamens are in a spiral form. And of course,
Tony, it's called Romanesco broccoli.
Is it? Romanesco broccoli, and I have had it. I just forgotten its name, but it is very pretty.
Very spectacular.
Yes,
You wouldn't want to cook it, really. You'd want to definitely serve that raw, keep its complete beauty in place.
And then, of course, in nature, things don't happen, as it were, by chance. There are the reasons why the shapes develop and the colors develop as they are, because normally the reasons are to do with the with advantages for flourishing. Really, they're somehow going to attract insects to pollinate them, or for some reason. And I don't understand this terribly well. Why? And I'd like to understand better why the spiral occurs in flowers. So if there's any botanists out there who'd like to explain it to us, wouldn't you like to know too, Caroline?
I'm not sure that there's a why. I think it's more of a fascination that the fact that it happens. I'm not sure that I've ever heard a reason for why it happens.
Well, you see, I haven't either, Caroline, but I believe that nature works like that. Well, Darwin's theories were all about evolution, the survival of the fittest and that sort of thing.
There is a village in Africa that has been designed on the same principle of that spiral going out, and that was the idea with that is protection is well, it was expanded that way, like the shell of the snail. And so it expanded as it grew, but that shape, I think, was related to the safety and security. But I'm only aware of one place in the whole world that uses it.
Well, we've just bought our youngest son for his 50th birthday. We've just bought him a spiral staircase in pieces, would you believe it? And so it's a 3D jigsaw puzzle for him to put this spiral staircase into his house. And it is absolutely beautiful. It's we talked about friezes a few weeks ago, didn't we, Caroline? Frieze patterns.
We did. Yeah,
and many of
patterns, not freezers, in case anybody was wondering. It's not about the cold things, it's frieze patterns, which are a nice long sequence pattern. Repeating patterns. There's a lot of geometry in them. And often they're used in ironwork for things like railings and spiral staircases. Okay, so let's go on to the next one. Now, here we have an image of, it is a spiral, it isn't a helix, on a spiral on a sphere. And so imagine this sphere with a North Pole at the top and all the swirls going into round and round and round and round into the North Pole, okay? And then trace with your finger or follow one of those yellow curves around and round and around until it finally goes into swirling around into the South Pole. Okay. Yeah.
Right. Now, also, they're not awfully bright, so some of you might not be able to see, but this image has got lines of latitude going, circles that go round on it, marked on it, like the equator, but getting smaller as the lines of latitude go up towards the North Pole or down towards the South Pole. And it's also got lines of longitude, which are what we call great circles that go through the North and South Pole. Okay, so it makes like a square grid pattern on the surface there.
Yeah, so I was working on figuring that out earlier. So the point P is actually on the surface of the sphere. It's one of those, let's say it could be a cross section of one of the latitude or longitudes on the surface of the
Well,
sphere?
at some point, all the points, why I was talking about the grid was that on the surface of the sphere, right, the edges of the grids are partly arcs of circles. Well, they're all arcs of circles, actually. And they're not exactly square, okay? But when you project, and as Caroline just said about the projection, we'll go over that in a minute. When you project that grid onto the horizontal plane, it becomes a precisely square grid.
And that's now, start from due north, as it were, the top, and then you go make a line from the top to a point on the surface of the sphere, and then take the straight line that down onto a flat piece of paper, and you can plot every point on the surface on a flat piece of paper.
Yes, and it's a two-way mapping, really, because you can map from the flat piece of paper, the flat plane. You can map up onto the surface of the sphere, and then P dash maps to P, and right. P dash PN is a straight line, okay? So you can map P to P on the sphere to P dash on the plane. It works both ways.
So you can find out what a shape on a sphere is on a 2D plane, and you can do it the other way around. You can draw a shape on a 2D plane, and then by using that technique, then place it on the plane, and it would be correct. It would be, that is what it would look like if it was on the surface of a sphere.
Now, if you drew a spiral on the flat plane with colored yellow, but with the same width, right?
So the width would be the same throughout. On a 2D,
yes.
on the flat piece of paper, you'd have a spiral that was the same width all the way.
And it went out. Yes, I think so. I'm not quite sure about the width thing. Maybe I'm saying the wrong thing. And it goes out and out and out, because you've got to imagine not just the piece of paper in my little picture there, but a piece of paper that goes out and out and out and out forever. Yeah. Okay, because in mathematics, although this is your dream, you can't do it in real life. In mathematics, you can reach infinity. Okay. Now the North Pole is projected to infinity, and all the other points.
Makes sense, because the North base, it does make sense, because the center point is just going straight down. So both of those spirals at the top and bottom of that sphere become one point. The two centers of the two spirals are one point on the 2D plane, because they go straight down through each other onto the 2D plane, and then. But by the time you finished, your angle would open up until you're actually at a tangent to to the top, to the north. And of course, that if you've got a line that's a tangent, it's going to go on forever. It's like it's a big parallel to the piece of paper.
Well, it's all very geometrical, and it's actually, I just photographed that from my book of Escher. Designs, and of course he was tremendously interested in geometry. Most of his designs are based on some sort of exploration of geometrical ideas, and indeed that's what he was doing here. And shall we next week do a whole hour on Escher, Caroline?
I think that would be delightful. That would be wonderful. I love Escher.
Let's do that.
We've got a new fan. I hope I get your name right, Curescu. I'm going to say Curescu. It might be wrong, but Curescu is delighted to discover the program, and it's a pleasure to see such an interesting math presentation. We do this every week, so 5 o'clock London time, same time every week, and next week we're doing Escher. Woo, I'm so excited.
Caroline, jingle.
Thank you, Tony. What would I do without you? Stay more focused, perhaps. Break, here we go. Oh, that didn't work. I've
really.
no idea. I've no idea how I did it, but I've now got the comments coming up on the screen, so you can see them too. Toni, can you see it?
No, I can't. So what are people saying, Caroline?
It's amazing. Kirescu said amazing. That's what I've I've told you basically. Govinda was attempting to help us with the name of the antlers. He said antlers, and he told us antlers. So
yes, it was the name. It wasn't the name of the. I did remember antlers, but it's the name of the particular sort of antelope. Because the eland, I think, has similar but spiraling antlers, but that isn't an antelope.
Yeah. It was when we were looking for the name antlers that he placed that on there. I didn't see it. Yeah.
Now, for those of you who are not British, you may or may not know that Celtic art, now they're the original Brits actually, and now they occupy Wales and Scotland and Ireland. So the Angles and Saxons beat them and push them out to the fringes. Anyway, the Celtic art features a lot of these sorts of patterns. This design you see here, I think I love it. If you start in the center of one of these spirals and wind out, you find that you actually go to the next one in a sort of S bend. It sort of, can you see, Caroline? Isn't it intriguing?
Yeah.
And if you look at Celtic art,
how many lines are there in all?
Well, you can answer that question later, Caroline. Anyway, we set it for our listeners to investigate, and also to look for more Celtic art as well, because it is beautiful. It's very geometric, and often, but not always, involves spirals. So there's an example for you. And now we have got the Fibonacci spiral. Now, we mentioned earlier that the Fibonacci sequence starts with 1, 1, and then you add the ones to get 2, and then you add 1 and 2 to get 3, and then you add 2 and 3 to get 5. Have you found these numbers on the screen? And then you add 3 and 5 to get 8, and 8 and 13 to get 21. And that's as far as this goes. But what we have here is a Fibonacci spiral. Now, I do recommend you draw this for yourself, because it is fun. And what you do is you get a piece of paper, and of course you can make it bigger if you want to. So what my question for you is, after 34, what's the next Fibonacci number? Well, I'm going to leave that for you. Okay.
See how big of a spiral you can make.
Yes, I mean,
where do you have to start? That's an interesting. Where do you have to start?
Well, it says on it. It's there on the instructions.
Yeah, when I give it that size paper, Toni.
Ah, well, you just have to. Well, you know, you start from one corner, 9 and 10 along and 6 up, because you unwind from there. You have to.
But that's if you're ending at 21.
No. Whatever you're going to end, you start at the bottom left-hand corner of your piece of paper.
Okay.
And you do what I said on what is on the screen. So you mark 2 squares at 9 and 10 across and 6 up. And then you draw a quarter circle as an arc on each of those. You can see how from looking at the diagram.
Mm-hmm.
And then you draw another square 2 by 2, and you draw another quarter circle, and another square 3 by 3.
And where does the 34 go?
You just carry on, Caroline.
But it goes below. It goes underneath.
Well, you'll have to work out which corner. Yes, Caroline, that is a good question, Caroline. You just have to work out which corner it is. It would actually be, if you went up to 34, Caroline, it would have to be just under bubbling, the corner you use to start would have to be at just under bubbly mass, which is now top right.
But then you've got, if you do the next one after 34, then you need lots of space to the left.
Around,
and then you need lots of space above if you go the next one. So the spiral keeps getting bigger. So that's my point.
Yes, but but each time you have to think about it, put it in the right orientation, and go to the bottom left-hand corner, wherever it is. You see what I mean? So
it's definitely true if you stop at 21, Toni. But if you're going further out, if you're making the spiral bigger and bigger and bigger, then
the corner to start with, if you do 34, is if you just added the piece of paper that's identical to this one underneath it, then you would. Well, we'll leave it to everybody else to work out. But you do take one corner and make it your bottom left-hand corner. That's what you do.
Okay. I'm challenging that. So, and we're not going to go further than that, but I want you to think about it. You want to make a bigger spiral than that. I want you to think about where to start it and let us know. Is where do you need to start it if you want to take?
If you start with the right corner, steps. Yeah, Caroline. If you start with the right corner, you have to go. Believe me, 9 and 10 squares across and 6 up. But you've got to decide which is the right corner.
If you went to 21, yes, I agree.
You do it, Caroline. Come back to me. Okay, now we can turn this into an elephant. Isn't this beautiful? He is just what we've drawn, but see. Near the middle at the bottom, that's the curve that we've just drawn, okay? And we've just changed it a little bit. So the next picture along shows how you take out the first three circles so that you get his trunk stopping. So it's the 1, 1, and 2 arcs that are taken out. And so the first arc is in the 3 by 3 square. And you also make his ear. So instead of having a quarter circle, you actually put a semicircle on to make his ear. And then you need a little dot for his eye. And there's the elephant. And we give that I didn't give it the name, but somebody gave it the name Elephant Dreaming, which I think is a lovely title.
And if you notice, there are different, you can use your imagination again to do different things. So you've got the elephant in the middle at the bottom, and you could actually make a big ear, one that goes all the way down to the bottom of the trunk, because an elephant's ear can go quite low down. And you've got the 3 different designs. You've got the black and white, the white and black, and then you can be creative with this, and it's a lovely way for young learners as well to get to colour in.
There's a school of opinion that do your artwork and fancy it up and change the maths, or there's this which of course you are doing here, but what you still have is the 4 quadrants and the semicircle, and then the little circle for the eye. So you preserved most of the Fibonacci, but not all of it, and you've got some geometrical shapes there. But as Caroline says, then use your imagination and go free and do whatever you fancy.
Without actually changing the proportions, I can see a parrot as well.
My goodness.
You remove some of it, I can see a parrot. So you can use the proportions as they are, but make different animals or different designs.
I can see I can see your parrot. Now your eye is still the parrot's eye, and your beak is still is sort of the semicircle, but I'm not sure about the rest of his. Anyway, Caroline, we should have a jingle.
Yeah, let's have a jingle. So my challenge is to find different patterns without changing the proportions. Go. Go. And oh, It's too sensitive. That's what I have to do. Not going to play it again. Go ahead. Go ahead, Toni.
Okay. Now, what I want you to imagine now is 4 lonely bugs at, now I know I can see 12, but I want you to imagine 4 lonely bugs at the corners of the big square.
Right. So there's only 4 bugs, and there's 1 on each corner of the big square. The others don't exist. The others
Not yet.
Not yet.
No, but in fact, they never exist. This is just a
path.
It is just a way to help you to understand what we're talking about. Okay.
Right.
Now, we've got 4 bugs standing at the corners of a square, and at the same moment, they see each of the other bugs, and then they look to their, well, they're going to go counterclockwise. They look at the next bug along, and they think, oh, I want to go say hello to him, and they start moving. Okay. They start crawling towards the next bug round, going anti-clockwise. And they all crawl at exactly the same speed, and they all keep the bug that they're heading towards in their sights, in a straight line, and they keep looking at the bug and heading for that bug. So by the time my bug at the top right, I should have numbered them, number 1, has got to the position 2. By the time he's gone a little way in, the bug he's watching, can you see he's gone a little way in? In fact, they've all gone a little way in. And so now, can you see the slightly smaller inner square that's tilted? So we've only got 3 stages of this pathway marked, but actually it's a continuous path. We've only just sort of taken 3 frames, as it were, and frozen them and put them inside each other, so to give you an indication of what's happening. So as the bugs crawl towards each other, they spiral into the center of the original square until they collide at the center. And they're always at the corners of some square, but the squares that they're actually at the corner of at any instant are getting smaller and smaller as they move inwards towards the center.
It's fascinating, and it's just imagining it. I find it is a very is a worthwhile activity. Just doing my best to imagine it. And I tell you what, you know, where I said you could draw it. You could draw like a, you know, like you do the line graphs that make patterns by joining points on edges, and that makes it look like a curve. This is hard. I have been attempting it to make a representation of it, and it's really hard. I haven't worked it out yet.
Well, I haven't worked it out either, Caroline, but I have it
on good authority.
No, not good authority, because there's lots of rubbish on the web, but I did find this on the web.
Oh, okay. And there is some good, you know where to look.
No, I found this on the web, and the claim was that they're Fibonacci spirals. So I think if you understood it sufficiently well, you could draw it rather like we drew the elephant's ear.
Yeah.
But I think that it is the elephant's ear, the elephant dreaming picture. It's more of a representation using the squares. It's the squares themselves that are a Fibonacci sequence. I think by drawing the arcs, we're not getting the exact spiral. And here we've actually got, sorry if that's disappointing, but here we've got, I believe we have got 4 Fibonacci spirals. But And they are self-similar. So we've got a sort of fractal here too, Caroline, because you see what we've got is self-similar squares at every instant of this picture. We've got infinitely many of them inside each other.
And it goes on forever because we can do that with our imagination. Conceptually, it goes on forever.
In theory, if it was just a point, of course, they would go on forever. But because they're big bugs, relatively, yet they all bunch up in the middle and then they have to stop.
Yeah, that's what I call the difference between an engineer and a mathematician. A mathematician could go on forever and an engineer will go, well, that's it. You know, we've reached the middle now, we can stop. Whereas a mathematician can go on forever.
Yes. Well, the source I got this from, which I should have quoted, of course, actually said, speculated about what was driving these bugs towards each other.
Okay, right.
Were they hungry, or were they lonely?
Well, anyway. Maybe they're 4 moths that are spiraling into a lamp. Apparently, a moth takes a spiral path into a lamp.
Apparently, moths take a path which is at a constant angle to if they're spiraling in towards the light. And there's a theory they believe it's the moon that they're going for. They take a constant angle between the direction that they're going in and the light source, and that ends up with them spiraling into the light. Now, what about this?
That is incredible.
Well, you'll see many. I mean, actually, hundreds of them. You'll see hundreds of these in the dynamical systems pictures, like the Mandelbrot set, but there are many of them. And this one is the simple mapping of the complex variable Z to the complex variable KZ. That's the Mandelbrot set. And this is just one picture from it. One little slide as you go on and on, zooming into it.
One moment in time.
Indeed. Isn't it amazing?
Yeah.
So these spirals occur because you've got here both a rotation and a dilation or a shrinking.
Yeah.
So they're going in towards a fixed point, which your eye can see down in the center there. And yes, it's intriguing and it's beautiful and it's complicated in the design. It's lovely. Yeah.
So now, and there we got the same again.
Well, similar, isn't it?
Similar, yeah.
This is actually a galaxy, and now there's apparently galaxies are spiral and they move around on these tracks, and they're more or less flat, which is quite surprising.
I mean, really, from the
absolutely flat, but yes, that's right. So this I do vouch for being accurate because this is from the Hubble side.
So looked at from the edge, they're more or less, but not. So we see this.
Well, there is some thickness
from the edge, some thickness, but
it's like a coiled rope.
It's like my coiled bit of metal.
Yes,
some thickness, because there's more thickness than my metal, but it's. If you looked at it from the edge on, you wouldn't see the spiral. You'd see more like a vertical galaxy, and you wouldn't see the spiral. I'm just speculating here. I don't know. I didn't know that it was only...
something like that. I'm not an astronomer, but the thing is, it's like your wire that you made the bubble to show us. It's like the coiled rope, of course, and like the cinnamon bun.
Probably more like the cinnamon bun, in that the cinnamon bun has quite a lot of thickness.
Yes, and this one is, and if you're at the astronomers out there, I'm sure there are none of them watching it.
Yeah, they're probably going, what are you on about?
We'll probably would say we're talking nonsense.
If you're watching this and you don't like it, please comment and correct us. We'd much appreciate it. Thank you.
So this is named NGC 6946 HST Subaru, apparently. There you go. And here, what about this one?
Okay, so Toni Curescu, I'm hoping I've pronounced. I don't know if you're male or female. I'm assuming female with that name. She's a teacher. He or she is a teacher in the Pedagogical College in Romania, in Iași, Romania, and she's going to present this video to her students from 9th and 10th classes next week.
Oh.
She's thanking us for the activity. Thank you.
Oh, that's amazing.
Let us know how it goes. Thank you.
One of my most wonderful, wonderful, wonderful students was Romanian. And he used to send, from the age of about 12, he used to send in solutions to enrich. And they were usually the best solutions that month. And he was in Romania, school in Romania. And then when he was, so if our friend is watching, should look at enrich.maths.org, and you'll still see a lot of Andrei Lazanu's solutions. And as he grew older, I became more and more impressed, because he pretty much every month sent in a solution. And so I talked to my friends, in particular to a Czechoslovakian friend, and he got a scholarship to Cambridge and came and did a degree here and then a PhD. And I'd love to hear from Andrei. I must try and contact him again, because he's now back in Romania. So Andrei Lazanu, a mathematician from Romania. Okay.
There's the link for you there.
Okay. Well, I'll try and put you in touch with Andrei. He's a lovely young man. Okay. So what have we got here? We've got a whirlpool. And this is a believe in the sea. But of course, you can make your own whirlpool if you watch the water going down a drain out of your bath. It'll go in a swirling round.
Yeah, it will.
And
by that as a child.
It is said, but it is denied by other people, that the water goes round clockwise in the northern hemisphere and anti-clockwise in the southern hemisphere. But I'm not sure I believe that.
I'm assured by scientist friends that it's a fallacy, that it goes the same.
Yes, it's an old wives' tale.
Yeah. But
something I do know to be true is that if you're canoeing along the river where there are rapids, in a canoe, okay, and I've done this with my husband. I'm not likely to ever do it again because I'm too old now. And it's brilliant, but it's not so much fun when you get into if you allow your canoe to get into a whirlpool where you whiz round and it's very hard to get out of it. So the skill is to avoid it. You're along the river, but just avoid it. But the current wants to suck you in. Okay, so I think our hour is up.
Yes, it is, Toni. Thank you for that beautiful final image. Oh my goodness, absolutely breathtaking. Thank you so much for joining us, Curescu. We look forward to you being able to join us every week. That's 5 o'clock London time. I'm not sure if that's 7 o'clock in the evening your time. And Govinda, as always, thank you. And we'll see you next week, 5 o'clock London time. And we look forward to it. Next week, we're doing Escher. Yes, Escher. I love Escher.
Goodbye, everybody.
Goodbye.